Welcome to this video. This is section 2.1, the basics of the joint point model, technical supplement. First, we will describe the equivalence of two parameterizations. One form of the joint point model is called general parameterization. It models each segment with a linear equation. Because the segments are connected, they must satisfy the constraints that force the connections at the joint points. In this example, there are two joint points. At the first joint point, tau 1 at 1973, the constraint is alpha 1 plus beta 1 times 1973 equals to alpha 2 plus beta 2 times 1973. At the second joint point, tau 2 at 1991, the constraint is alpha 2 plus beta 2 times 1991 equals to alpha 3 plus beta 3 times 1991. The other form is called standard parameterization, which can be written as one equation like this. It starts with the first segment beta 0 plus beta 1 x, and then add to the slope by the amount of delta 1 at the first joint point 1973 for the second segment. And finally, add to the slope by the amount of delta 2 at the second joint point 1991 for the third segment. The indicator function I of x minus 1973 is defined as 0 if x is less than 1973, and 1 if x is greater than or equal to 1973. Similarly, for indicator function I of x minus 1991, it is 0 if x is less than 1991, and 1 if x is greater than or equal to 1991. When we write out the equation, we can see that for the years between 1969 and 1973, the model becomes beta 0 plus beta 1 x. For the years between 1973 and 1991, the indicator function I of x minus 1973 is 1, while the indicator function I of x minus 1991 is 0. Therefore, the model becomes beta 0 plus beta 1 x plus delta 1 times x minus 1973, which can be rearranged to beta 0 minus 1973 delta 1 plus beta 1 plus delta 1 times x. For the years after 1991, both indicator functions are 1. So we have every terms in the model, and it can be rearranged to separate the intercept and the slopes. Note that at the joint points 1973 and 1991, the adjacent segments connect. At 1973, the fitted value derived from the second segment is beta 0 plus beta 1 x, which is the same as the fitted value derived from the first segment. Similarly, for 1991, the fitted values from the second segment and the third segment are identical. When we compare the two parameterization forms, we see that the two forms correspond to each other. Beta 0 is the intercept of the first segment, corresponding to alpha 1. Beta 1 is the slope of the first segment, corresponding to beta 1 in the general form. The intercept beta 0 minus 1973 delta 1 corresponds to alpha 2. The slope beta 1 plus delta 1 corresponds to beta 2. Similarly, we see the correspondence in the third segment. Under the standard parameterization, we will be able to fit the joint point model by regular regression method. Each data point can be put into this parameterization. The matrix shows all the data points. The data points are Y1, Y2 to Y32, which are modeled by a matrix times a vector of parameters. Pay attention to the third column. The third column is x minus 1973 times I of x minus 73. Therefore, for the observation occurs at 1969. The third column is a 0. For the observation at 1974, it becomes 1 in the third column, and then it increases to 27 for year 2000. Similarly, for the last column, for the years before 1992, the values at the last column are 0. It becomes 1 starting from 1992, and it increases by 1 every year up to year 2000. Therefore, assuming the number and the locations of joint points are known, we can fit a joint point model using a regular regression method. Therefore, the parameters beta 0, beta 1, delta 1, and delta 2 are estimated by the least squares method. We now explain relation between APC and the slope beta. For a log linear model, expected value of log of y is equal to alpha I plus beta ix for the ith segment. So expected value of y is approximately equal to exponential of alpha I plus beta I times x. APC is defined as expected value of y given x plus 1 minus expected value of y given x divided by expected value of y given x times 100%, replacing expected value of y given x by exponential of alpha I plus beta ix from the model. We can see that APC is approximately equal to exponential of beta I minus 1 times 100%. This is the end of section 2.1 technical supplement of the basics of the joint point model. This video is produced by NCI joint point model team. Thank you for watching.